Shown in the figure below is a grindstone with a mass of 80 kilograms and a radius of 0.7 meters. It's used to sharpen an axe. The axe is pressed against the spinning grindstone with a normal force of 20 newtons. When this is done, the grindstone slows from an initial motion of 100 RPM and comes to a stop in 2 minutes. This is a kinematics problem followed by a force problem. Let's begin with the kinematics and extract well-formed information from the problem. 100 RPM. RPM stands for revolutions per minute, and since this is a distance over a time, we recognize that this is a velocity. Since we're told that this is the initial moment, we recognize that the 100 RPM is the initial velocity. Although this is a well-formed expression, since the initial velocity is indeed a constant and can be set equal to a number, the units on this number are poor because we would prefer to do all problems in radians per second rather than rev per minute. So we need to perform a unit conversion. I'll begin by eliminating the minutes by putting them in the numerator and replacing them with the preferred unit of seconds, and we decide that 1 minute is the same interval as 60 seconds, thereby canceling the minute unit and leaving behind seconds. The other problem with this expression is that there are revolutions in the numerator, so we will need to put revs in the denominator and replace these with their preferred unit of rads. And we recognize that 1 revolution is a complete turn and therefore represents 2 pi radians, meaning that we need to multiply our 100 rev per minute by 2 pi, divide by 60 in order to get the desired units to have 10.47 rad per second. The next bit of information supplied in the problem is that the wheel comes to a stop in 2 minutes. Clearly the 2 minutes is a time, and I'm going to convert it directly to seconds to be 120 seconds. This is ill-formed information since t cannot always be 120 seconds. T is 120 seconds under a special condition, and that is that the wheel has come to a stop. If this were linear motion, we might be tempted to set v equal to 0. However, since it's rotational motion, stop means that omega is equal to 0. This last expression is simply begging to be plugged into the relationship between omega and t, and we'll do so before we proceed with any of the other parts of the problem. The omega t relationship is this one. Omega is omega 0 plus alpha t, and plugging in the quantities we know, we'll put 0 for the angular velocity, having begun at 10.47, experiencing an unknown alpha over the time of 120 seconds. The only unknown in this equation is alpha, and alpha turns out to be 0.0873 radians per second squared. We've been led to this result simply by following the well-formed information that the time of omega equals 0 is 120 seconds. However, we've been rewarded since this is indeed the answer to part A. We can now proceed to part B, which asks, how many turns does the grindstone make before coming to rest? Turn is an angular distance, and so in fact we are trying to find a value for theta. Theta equals what is in fact the question where, and that is an ill-formed question until we repair it. We can repair it in one of two ways. We can ask for the theta when omega is equal to 0, because that in fact is exactly what it means to come to rest. We can also use the fact that we've been told in the initial formulation of the problem that this takes 120 seconds. Either one of these formulations, using the theta omega equation for the first one or the theta t equation for the second one, will yield us the correct answer for the number of turns that the grindstone has undertaken. Although I don't have a preference, I'm going to solve the first of these two by beginning with the theta omega relationship, which is omega squared is omega 0 squared plus twice alpha theta minus theta 0. The Vx relationship with all x's changed to thetas, all v's changed to omegas, and a's to alphas. Plugging in the values we know, and particularly omega equals 0, our only unknown will be theta. Indeed, that's the case, and so we get the result that theta is equal to 628 radians. However, since we've been asked for turns, we need to perform a unit conversion. We would like to cancel away the radians and leave behind turns, and we recognize that 1 turn, which is a full cycle, is the same angle as 2 pi radians. Therefore, we get the result 100 turns. Let's move on to part C. In part C, we're asked for the moment of inertia of the grindstone. Well, the grindstone is a shape that we remember. The grindstone is in fact a solid cylinder, and the moment of inertia of any solid cylinder is half the mass times the radius squared. Since the mass is 80 and the radius is 0.7, we get the result 19.6 kilograms meter squared. Finally, we're asked what is the coefficient of kinetic friction between the axe and the grindstone. Let's take a look at the diagram and see if we can understand the meaning of this question. We realize that the reason that the grindstone is spinning to a halt is that our normal force of the axe against the stone wheel has generated a friction. If we only had a normal force, that normal force would serve to neither speed up nor slow down the grindstone. However, the friction, since it will oppose sliding, will generate a torque, and the torque will cause the grindstone to come to rest. We know that the normal force is 20 newtons, and so the force of friction is going to be mu k times the 20 newtons, and that will assist us in setting up the torque equation that we need for part D. The torque equation is the rotational equivalent of F equals ma, and is therefore torque equals I alpha. We've already determined I to be 19.6 and alpha to be 0.0873. As we mentioned previously, the force responsible for creating this torque will be the frictional force, and the frictional force will be mu k times a normal force of 20 newtons. However, this quantity is merely the frictional force. It is not a torque. In order to convert a force into a torque, we need to take force times radius. And since the radius of the grindstone is 0.7 meters, this expression is now the torque due to the frictional force. As you'll notice, there's only one unknown in this expression, and so we can solve directly for the coefficient of kinetic friction between the axe and the grindstone, and the result is 0.122. And as always, coefficients of friction are unitless.